Well, let's begin our next seminar. Today, our speaker is Professor Roberto Musina from the University of Udine. Please, you can start.
Okay, thank you. And of course, first of all, I have to thank the organizers, Daria, and in particular, my collaborator and great friend, Alexander Nazarov, Professor Alexander Nazarov. I will report on some recent joint paper in collaboration with Gabriele Cora. He is a postdoc at the University of Torino, but he was in Udine during COVID time, so we started work now, basically. I will talk about apparently simple geometrical problem, which also has some motivations arising in mathematical physics, and in particular, it is related to some problem raised by Arnold, concerning the motion of an electrified particle in a magnetic field. I will present an existence result, but in fact, I'm more interested in the understanding of the lack of compactness phenomena that can be observed when dealing with the energy functional is associated to the geometrical problem, let me say. And since I will repeat several times some words like lack of compactness or Palais-May condition, so on, let me very quickly fix some basic idea you can use if you want to use variational methods to solve equations like that, where E is a reasonable function defined, for instance, on an Hilbert space or an open subspace of the Hilbert space, and how to assume that E is not, of course, lower nor upper bounded. And how to solve this equation. Okay, one way is to study the energy sublevel of the energy functional, hoping to find a spatial level C, a spatial real number C, such that some change in the topology can be observed when passing from an upper so this is in this simple draw, this is the energy level E equals C plus epsilon. So this is the energy sublevel. When you cross this energy level C, you can assume that you can observe some change in the topology of the energy sublevel. Well, this change in the topology might be produced by the existence of a critical point here. So a solution to your starting equation having precisely the energy C. Of course, this does not happen always, because you might have some troubles with so-called, they are called now critical points at infinity, okay? But this strategy works if you have enough compactness at the energy level E equals C, and in particular, if the Palais-May condition holds at the energy level C. What does it mean? It means that whenever you have a sequence satisfying those two conditions, which is usually called Palais-May condition at the level C, then you can find a subsequence which converges strongly to a point in the domain of the energy functional. And in this case, surely U is a solution of your starting problem. And also you have one information on the energy of the solution U. And how to prove that some Palais-May condition holds at some energy level. In general, the first step, and in most of the problems, the first step comes for free. You try to prove that UN is weakly compact, that is bounded. And the second step in general is the hardest one, and in this case, and then the final step is to prove that in fact you have strong convergence. In the geometrical problem I will present you, the most difficult step is this one, concerns the boundness of Palais-Mail sequences. Okay, aiuto, my God. Okay, so let's go slowly and slowly to the presentation of the problem I started with Gabriele Core. Actually, I propose a very general problem. I could have been even more general than what they stated here. I will deal with the problem of prescribing curvature. So assume that you have H is a given reasonable function on the Euclidean space, and you look for an embedding from the sphere into the Euclidean space, having mean curvature H at each point. Of course, this problem can be faced from different point of view, and of course, this problem, general problem, has surely an answer if H is a constant, because no solutions exist if H is 0, and solutions are spheres. When H is a non-zero constant, that because of celebrated Alexandrov result. So I will always keep in mind, please, that I will always assume that H is not constant. In my professional...
Excuse me, Roberta, yeah. Are you assuming that H is positive, or it can be sign-changing?
Okay, it can be sign-changing in the results I will present.
Okay, thank you.
Okay, it happened that in my life, scientific life, I studied for long time the case of H bubbles, that is when H is the functions of on R3, and you look for a two-dimensional object surface, closed surface of the type of the sphere, which has curvature H at each point. And this since my laureate thesis. But then after several years, I learned that this apparently too simple problem was not so simple. And in fact, okay, the case of H bubbles is surely more challenging than the problem of the existence of H loops. But the two problems share some non-trivial, have the same non-trivial difficulties. So one can learn something by studying the case of n equals 1 and trying to then to do something for the more difficult and even more studied problem of the H bubbles. Both the problems can be the geometrical problems can be translated into differential equations. This is a system of two ordinary differential equations, and this is a system of three elliptic equations. Both the problems have a variational formulation, that is weak solutions, at least, can be found as critical points of some energy functional. The domains, of course, are different. The shapes are different in the two cases, but the two functions have some common features.
Excuse me, what is I in the first line?
I will, okay. This talk is mainly focused to the case n equals 1, so I will explain in detail all the blue line and in a moment. Okay, so everything I hope will be clear, and I will give an explicit detailed description of the energy functional which is associated to this system. But first, please let me say something very quickly about the more difficult problem of H bubbles. There are many results. Let me say that when H is a constant, non-zero, then the problem of H bubbles is completely understood thanks to this paper by Brezis-Coron, 1985. Well understood from the variational point of view. I mean, it means that the critical points of the energy functional, in case H constant non-zero, are completely classified, and also the behavior of Pallas-Mail sequences for this functional is completely understood. By the way, it's clear that from what I was saying at the beginning, that the functional EH does not satisfy the Pallas-Mail condition for several reasons. And in fact, I worked a lot on this problem in collaboration with Paolo Caldiroli from the University of Torino. We have some papers together, and we studied for a long time. As you can see, the H bubble problem, I will not list at all those papers, but I just want to mention this one. This is not surely our smartest paper, but with this paper we understood something about the compactness properties and the loss of compactness of the energy functional for the H bubble problem. So this is a not compact problem, always H bubbles, so H is the given, the prescribed, I missed, no. H is the prescribed curvature, mean curvature, is a function from Rp to R. The energy functional has this shape. I will not enter into the details of the definition of this, which is an algebraic volume with the weight H of the region of R3, which is enclosed by the surface parameterized by U. While this is the standard Dirichlet integral, it bounds from above the area of the surface parameterized by U, and in fact it is equal to the area parameterized by U when U is a conformal function from the sphere into R3. Okay, there are several technical problems. Algebraic means that you have to take into account the orientation of U, so this volume might be positive or negative depending on the orientation of U. This is the correct space. It's a Sobolev space for function from S2 into R3. There are many critical technical difficulties. The functional is not Frechet differentiable. This functional is not even Gateau differentiable in any point, but nevertheless, those are technical difficulties. The main difficulties are due to the fact that a lot of non-compact transforms acts on this problem. First, whenever H is, then H, the energy is invariant with respect to Möbius transform. This surely produces some lack of compactness phenomena. Using these invariances here, you can easily construct Pallas-Mail sequences. Okay, one can understand that there might be Pallas-Mail sequences which are not compact, but this is a kind of loss of compactness which which is observed quite often in critical problems. For instance, they are reminiscent of the loss of compactness what one can observe in Pojaev problem. I'm referring to the famous paper by Bresis-Nierenberg. Then the target space of trial functions here is R3. This is not compact, and in particular we have translations in the target R3, and also this group might produce lack of compactness phenomena, even if in general the energy functional is not invariant with respect to translations in the target space. Okay, it is invariant if, basically if, and only if, basically, H is constant, the prescribed curvature, which we are not interested in the case. But also those, that lack of compactness can be easily understood and faced by using tricks or arguments or ideas which have already been observed in different problems, critical problems. We learned with that paper that the worst lack of compactness phenomena are produced by the non-compact group of dilations in the target R3, even if in general the energy is not invariant with respect to dilation, say T is positive in R3. Using this group of dilations in that paper, we were able to exhibit dramatic examples of non-compact Pallas-Mail sequences. And those examples are dramatic because the Dirichlet integral of the Pallas-Mail sequences goes to infinity. The area of the surfaces parametrized by the Pallas-Mail sequences go to infinity. And actually, we do not know how to handle such a lack of compactness. In fact, there exist Pallas-Mail sequences which are not relatively weakly compact. They are not bounded at all. Those examples, we can exhibit those examples. In all those examples, some constant mh is greater or equal than 1, and mh is this quantity. You can see that this mh as an L infinity norm, or weighted L infinity norm of what? Of the radial derivative of the prescribed function. So let us think that H is C1. The prescribed function, curvature function is C1, just to fix ideas. In contrast, when this constant is strictly smaller than 1, then something can be said. It took 4 years and 3 papers to give a complete description of the behavior of Pallas-Mail sequences for the energy functional in the case mh smaller than 1. Of course, we also need to assume something else, but don't mind, this is not important. The problem is technically quite difficult, I would say. And please note, and also under this assumption, we have some few existence results. I don't know any other existence result for the H-bubble problem in a parametric form when H is not constant. Those are the only I know, besides some perturbative results. Okay. Please notice that this first existence result under the assumption MH smaller than 1 is from 2002, much before than 2006. And in fact, in that time, we were thinking that the assumption MH smaller than 1 was just a technical assumption. We met it by chance, while in fact, it is a basic assumption. Okay, I will stop here this overview about the H bubble problem because, in fact, in the paper with Gabriele, no, I have to say another fact. This assumption about MH is quite disappointing. And in fact, also with Andrea Malchiodi, we tried for a long time to remove or to improve it. Please notice that this is not an assumption on H at infinity. It's an assumption on H everywhere on R3, and it is a strong assumption. Okay, this is the problem. In fact, I started with Gabriele Core in this last preprint. With respect to Yau's problem is the case n equals to 1. And I stated again in this dimension. So H is regular, continuous at least, and we look for closed curves in planar, in the plane, planar curves having mean curvature H at each point. And now I write again the ODE I already wrote before. So this is a system of two ordinary differential equation of second order, because we look for functions U. Basically, U is a 2π periodic function, but you can see it, look at it as a function on the unit circle. And this is the scalar speed. This is the prescribed curvature composed with U. And I of U is the rotation of the plane. So that, we take some complex notation precisely, okay. U prime has the direction of the tangent vector to the curve, so I of U is orthogonal to the curve at any point, okay? Why this is the correct system to study the geometrical problem? It's quite easy, because if U is a solution, a 2π periodic solution of this system of differential equation, simply by multiplying by U prime, the scalar product, this is the scalar product in R2. Of course, the scalar product of U prime with I of U prime is 0. And so you infer that U have a constant scalar speed, okay? And if U is non-constant solution, then U prime is always different from 0. It means that U is a regular curve. Regularity issues for this ODE are easy. So if U is reasonable, then U is regular as much as the given function H allows. And also you easily obtain from well-known formulas that at any point the curvature of U at any point theta is equal to H of U of theta. Of course, there might be self-intersections. So the geometric regularity is, I will not enter into those tools of geometric regularity. As I said, I always assume that H is non-constant because otherwise the problem is trivial. Solutions are circles if H is non-zero constant, and do not exist if H is a constant. This problem, this ODE system can be studied via variational methods. The correct space is this one. Functions on S1 are basically 2π periodic functions. So this is the reason why I will always denote by shortness by H1 pair the Sobolev space of functions in H1 with values in R2. And the energy functional has two pieces, precisely as in the case of the H bubble problem. Okay. The first term which will enter into the energy is this pseudo length, let me call it pseudo length, is something which bounds from above the length of the curve parameterized by u up to this constant. Here, of course, this means that I take the mean. Okay. And it is convenient to take the mean here because this simplifies some formulas. It's not important. Trivially, this is continuous functional. It is differentiable on this set, which is the set of trial functions which are not constant. And it is an open subset of H1. And here is the differential of the pseudo length. This is an equality in the dual space. Some dual space, it's easy to compute. Then we also needed to introduce an H area functional for the H bubble problem. We had an H volume functional. So here I assume that H, let me say that H is smooth, C1 for the moment, but this is not needed, in fact. And assume that you take any vector field in R2 whose divergence is H. Quite easy. For instance, Q01 is a function of two variables. You can make this choice in the T, and this for the first coordinate and this for the second one. So no troubles for that. There is a variety of vector fields you can choose, in fact. And the area functional is defined via this formula. Okay, this measure the algebraic area enclosed by the curve with weight h. This claim seems to be quite not so clear in this moment, but I hope it will be clear in a moment. It's algebraic because you take this area with a plus sign and this area with a minus sign. Okay, yes. But don't mind about this. I will come on this geometrical meaning in a moment. But you can make some computation by hand. You can see that this functional is C1 on the full Sobolev space, and its differentiable is proportional to the normal vector here, to the normal vector of the curve, and the proportional function is U composed with the prescribed curvature. From this formula, and since evidently the area functional vanishes on constant functions, you can see that the functional A written here does not depend on the choice of the vector field you use here. And finally, if the total energy is this function on the Sobolev space H1 pair, is given by the sum of the two previous functionals, and because of those two equalities, we see that the functional is Frechet differentiable on the set of trial functions which are not constant, and here is it's Frechet differentiable for any function here. And so you can see that if you are able to find the critical point for this functional, then U is a weak solution to this system of ODE. The regularity issues for ODE is easy. In fact, it's easy to show that U is C2, for instance, if H is continuous, say. And the same argument as in the previous slides can be used to show that U prime, in fact, has constant absolute modulus, and hence U prime is also equals to the length of U. because of the mean, and so U surely is a non-constant solution to the system of ODE I present, and so it is an H loop. It has a constant prescribed curvature H at any point. So our goal is to find the critical points for this energy functional. We have some troubles, of course, otherwise I would not study this problem. We have some troubles with lack of compactness. What I say, it's not difficult to invent assumptions on H for which EH must have, for instance, a structure of mountain pass type, to invent assumptions that guarantee the existence of a change in the topology of the energy sublevel for some at some energy sublevel. But surely we have troubles with lack of, or we might have troubles with lack of compactness, despite the fact that differently from the H bubble problem, we have the compactness of the embedding. Any bounded sequence here converges uniformly here up to subsequence. Why we still have troubles with lack of compactness? Because the target space here is non-compact space. Here we have the group of translations in the target space, and most of all, we have the group of dilations in the target space, which produces lack of compactness phenomenon. And again, the worst lack of compactness phenomena are due to the group of dilations in the target 3. And even if the H bubble problem looks much more simple than the H loop problem looks much more simple than the H bubble problem, we in fact can construct, and we construct in a paper with Gabriele, Pallas curvatures H for which the energy functional has Pallas-Mail sequences which are not weakly compact, because the L2 norm, the pseudo length, this is basically the pseudo length of the UNs goes to infinity. Their length goes to infinity, in fact. Here is the picture of the graph of the prescribed function H. We explicitly exhibit. This function is 1 outside the circle of radius 1. And so this curvature has non-bounded sequences, admits Pallas-Mail sequences which are unbounded because their L infinity norm is unbounded, simply, and their L2 norm is unbounded, simply because you take here a circle. So this is the image of one of the UN. UN goes to, so UN is the identity plus a sequence that goes to infinity. Those are in fact critical points for H, because H is constant equals to 1, and those are critical points for H. Their norm, L2 norm, goes to infinity. So this is an example of Pallas-Mail sequence which is unbounded, but also with a lot of care, we have this circle of radius 1, which is again an H bubble for the explicit curvature we present here, but it has, so let me call it U naught. U naught is basically the identity, okay? And what happens? It happens that the energy of U naught is 0. So you can parameterize this circle several times, obtaining a Pallas-Mail sequence actually a sequence of critical points, but don't mind, it's a Pallas-Mills sequence for which the sequence of the length goes to infinity. And this can be done whenever MH is greater than 1, when MH, please notice, has exactly the same shape as in the H-bubble problem. So it is a simple problem. We have the same lack of compactness phenomenon with the same constant MH involved. And even if this problem seems to be much more easy than the H-bubble problem, the only existence results I know via variational method needs MH strictly smaller than 1. And I was not able to improve this assumption nor to provide an alternative to this assumption since a long time. But finally, we succeed in at least replace this assumption, which is really very restrictive, with another assumption on the curvature. Okay, the problem, the existence theorem, which I know it is from mine, it is in this short paper, in which in fact the existence part is not so important. I deal with different questions. It's not so important because the argument to get existence I use here is a copy and paste and simplified version of this existence result for the H-bubble problem. So the assumptions in that paper were those 1, H is in C1, this constant is smaller than 1. Then we have a behavior of some assumption on the behavior of H at infinity. H is asymptotically equals to 1. But I'm more interested in this assumption. The second one allows us to prevent the lack of compactness due to translations in R2. But this is the assumptions I was trying to modify or to remove, and in fact, we succeed from an L weighted L2 L infinity assumption, kind type assumption. We arrived in this paper with Gabriele Cora to a weighted L2 assumption on the radial derivative of the prescribed curvature. Also, because of our approach, we can pass from H, C1 to H continuous. And this is not totally trivial. I mean, because it's not easy to take the first theorem and to approximate, to use an approximation argument to get the result for H continuous with some meaning for this. Okay, the conclusion on the new theorem is that if those three assumptions are satisfied, then there exists a loop having curvature H at any point, and we are happy. A remark, this second assumption have been, okay, here I wrote the same assumption as in the older result because I'm not very interested in the lack of compactness due to translations, but in the paper with Gabriele, we definitely improved it in a significant way. But this is not very important for this talk. What I want to say that even if H is of class C1, then the two assumptions, the old assumption and the new assumption, are not comparable. Everything can happen, and we have some explicit examples. And the second remark is about the improvement of the second assumption, but definitely don't want to discuss this. A remark on the assumptions and on the proofs. I'm so sorry because I started to take time, but then I forgot to use the clock. So please, Sasha, let me know when it's almost time to finish. Okay. This assumption MH smaller than 1 enters in several points in the proof of the existence result. It strongly affects the properties of the energy functional, because, for instance, the Neari manifold in this case is smooth, it's a natural constraint, the mountain pass energy level is equal to the infimum of the energy on the Neari manifold, and moreover, a lot of other technical but useful facts hold under this assumption. While in the paper with Gabriele Cora, we only have C0, and the Neari manifold is not even a smooth function. Of course, I should say, and I will say in a moment, what is this object when H is only continuous, and what is this integral? But I will do it in a moment. Because we give a distributional definition of this object for H continuous. We, as the title of this talk says, to play with this constant, we use a Hardy type inequality. That's quite surprising to me. This allows us to study Palais-Mel sequence and to finally prove an existence result. I think that I have to go quite quickly on this part. Please recall that with this D, this is a first order differential operator. If K is a smooth function, this is modulus of zeta part radial derivative of K. Okay, and instead of explaining what is this, I will explain what is gradient of K zeta zeta. So in the assumption, relatively to the assumption of the existence theorem, K vanishes at infinity. This is the formal adjoint of the operator dk, because of integration by parts tells you that if K and phi are smooth, compactly supported, then the integration by parts tells you that dk phi is equal to K d star phi. So they are L2 adjoint, let me say, at least formally, okay? And once you have observed that this equality holds for K smooth and phi smooth, it's quite easy to define those two operators for K in L1 log. This is, can be done in a standard way. And when I say that dk for L1 log, dk is L2, I mean that dk, the distribution dk, is represented by a function in L2. Okay, but I will simply write dk in L2 to mean this fact. So very standard, and perhaps this density result is okay. Once you have defined a D and D star, you can introduce this space, give a norm on this space. It turns out that hat D1 is a Hilbert space when endowed with this norm. I don't know, surely, for instance, Alexander can understand what I'm writing here. This is a larger space because here only the radial derivative of K enters, and I do not so the K might be very, very bad on spheres, okay? This is perhaps the main result, in a sense, one of the main points in the proof of our theorem. It is this density result, which is not trivial at all. Why? Because when you try to prove a density result for Sobolev type spaces, of course, you take a function k, the Sobolev type space, a sequence of modifiers, and try to prove that k convolution rho epsilon goes to k in the norm you want. Surely this is true. In this, you have this convergence in L2, elementary. Since dk is in L2 by the same elementary factor, this is in L2, but you have to play with weights inside, okay? And surely this operator D does not commute with convolution. So the density lemma is not trivial, but if you take a sequence of radially decreasing modifiers, then you can, in fact, conclude with this density result. Why? Because if the rho epsilon are decreasing, then minus d rho epsilon is a non-negative function. And also you can use integration by parts, okay, to see that minus 1/2 d rho epsilon, which is a non-negative compactly supported function, has L1 norm equal to 1, because this is true for the rho epsilon. So as a consequence, we have that also this is a sequence of modifiers. And then, okay, you make some computation, more and more integration by parts, and you obtain this equality. And at the end, you are done, because you can write this same infinity function in this way. D star is in L2. Okay, D star is in L2. Recall that D star phi for a smooth function is minus the divergence of phi of phi of zeta zeta. This is by definition. This converges to D star k in L2. And so this converges to 2 times k in L2, because k is in L2 as well. And at the end, you obtain the conclusion that is that, in fact, d of k convolution rho epsilon converges to dk. And this density result has many corollaries. dk has the same L2 norm as d star k, for instance, and because this is a triviality when k is smooth, and then you can use the density lemma. And also we have this RD inequality, which is the core of our approach. Okay, this is nothing but a very well-known Hardy type inequality when k is infinity with compact support. It calls with a strict inequality, but functions here to be, so the fact that k is here in a sense means that k has some regularity only on radial directions, and can be very bad on direction on spheres. Okay, I will skip the proof of this, which is, sorry, oh my God. I skip the proof of this. This corollary seems very evident, but it is not unless you have the density result you need. Okay. Okay, how to more and more consequence of the density result is this lemma, in which we say, Alexander, how many? I spent
moment.
It's 25.
15.
Ah, no, this is not the 15. So let me take, according to... Okay. I'm not so late. Okay, great. So the density...
If you wish, even 20.
No, okay. No, I was thinking 5, so I was terrified. Okay, so the density lemma, we have as many, so let me, many consequences, and perhaps the main one is this Hardy type inequality. Okay. Okay, recall that this is gradient of k of zeta dot zeta squared, and the best constant is precisely 1. It is not achieved. But the density result has another consequence, which is stated in this lemma. So now assume that H is a continuous function, non-constant. Assume that this distribution, which is the distribution dH, is in L2, and that H minus 1 vanishes at infinity with this rate, at least, okay? Then we have that H minus 1, in fact, is in L2. Of course, this assumption is not enough to have that H minus 1 in L2 is almost enough, but it is not enough. You also need this fact. And in fact, this plus this implies that H minus 1 is in the Sobolev, weighted Sobolev tie space I introduced before. And hence this inequality holds with a sharp constant and with a strict sign, because H is not constant function. What about the assumptions which are written here? I don't remember. Surely you cannot remember, but the function example H in the existence theorem is okay. Okay. We have more assumption in that theorem, but for instance, this lemma can be applied to H, satisfying the assumptions in the theorem. And the proof is, I don't want to bore you with the details. You have to be a little bit careful in choosing cutoff functions, so on, but basically the core of this lemma is again the density, basically the density result. Okay. Now, in this is about what all we need about the operator D applied to a function as in the existence theorem. The second point, main point in the proof, concerns a deep studying of the area functional, and to prove related estimates via Hardy inequality. and via the introduction of the constant nh. So we have to go inside to the definition of the area functional. So recall that in the theorem H is equal to 1 at infinity, and the area functional was given by this formula whenever Q is a vector field whose divergence is H. Okay, this formula is fine for H C1, but our H is always C0, but I don't want to enter into details. I mean, we can split by linearity this area functional in two area functionals. The first one is related to the constant curvature H equals 1. And the second one is related to the non-constant, let me say, part of the prescribed curvature. Okay. The constant part, so the area functional relative to the constant part is very nice. You can it's this functional because the divergence of 1/2 zeta is equal to 1, and it is by elementary argument one can see that A1 is in fact analytic on the Sobolev space, and also since we need estimates, you obtain the classical isoperimetric inequality. Pi it does not appear here because pi is inside the means. I use everywhere, but this tells you that the area inside the curve is controlled by the square of the length. So this is a very classical isoperimetric inequality. Of course, if our paper contains some novelties, those concerns the non-constant part. So let me handle the non-constant part. For shortness, I denote by k h minus 1, so k vanishes at infinity. Basically, it is a continuous function, and instead of talking about a of h minus 1, I would talk about this area functional for the curvature k. This is explicitly given again by any vector field Q whose divergence is K. This is the explicit formulation. And I can take, as I said before, any vector field satisfying this equation. So for instance, I can remember the explicit solution if K, recall that, by the way, recall that K is in L2 by the lemma, proved via the density result. So I can recall this well-known formula. We are in 2 dimensions, so this is correct. And the Laplacian is the divergence of the gradient. So for instance, I can use this blue function to compute the area function at U with weight K. In this light, you can think that K is C1, don't mind. C1 and in L2. Okay, so let us make this choice. The area functional with weight K is given by this integral 2 pi, 1 of 2 pi. Here I have the mean. This is the scalar product in R2. This is the normal vector, and this is the function in blue here. And of course, everything goes so smoothly that I can use Patou's lemma to change the order of integration. So this is first an integral on R2 of k, and here is the remaining part, compute some function computed at u minus zeta. This blue function is something that is well known. because for at least for any point zeta, which is not in the image of U, here or here, J, this blue functional, including the integral, is the winding number of the function from S1 into R2 minus 0, which is given by U minus the point zeta in R2. And in particular, this is an integer number. So for given fixed U in the Sobol space, for instance, most infinity is the same, I find an integer valued function, Ju, call it Ju, for which the area functional has this shape. And recall that K is indel2 by the lemma. So if I wish to have estimates on Rk, I just need to have estimates on this winding function. And in particular, I like to have L2 estimates. And this is something that can be done. There is this basic estimate. I have to say that these are not, from now, not original ideas from my paper, but the ideas here come from Stephen paper about 72. He was dealing with, not precisely with the H-bubble problem, but with the plateau problem for disk-type surfaces having prescribed mean curvature. But that problem is much more difficult, but the basic idea are here. How to obtain estimates on this function J of U. This is the great idea by Stephen. Instead of fixing fixing K and look at the area functional as a function of U, it's better, accordingly to Stephen, to fix U and see this as a linear function of the curvature K. More precisely, it is even more convenient to identify K with a 2 form in R2. So K is let's say that K is a smooth compactly supported function. We can because of the density result. So this is a smooth infinity form, 2 form on R2, and we can associate to this 2 form a real number. Because U is fixed. U is fixed, and hence we have a linear function from 2 forms into R, which is continuous, some computations, and so this is what Federer calls a 2-dimensional current on R2. Now, using the fact the dAKU is equal up to a constant KU I U prime. Using this fact and using the 31, the statement number 31 of a theorem in the last, perhaps, chapter of Federer's book, Geometric Measure Theory, finally, you obtain this nice estimate on the L2 norm of this function. So those are the accounts from Stephen by Honesty, and this inequality have been proved also by Camona Ruffi in this, unfortunately, nowadays minor journal, which is Rendiconti del Circolo Matematico di Palermo, is, I guess, the first mathematical journal in Italy. But the paper is quite recent, and their proof is very, very long. I find that this is much more. Oh, okay. To conclude, if I take H as in the statement of the theorem, okay, you can see that, okay, here I have even less restrictive assumption. First result, I can express the area of the non-constant part of H in this way through the winding function, which is written here. Moreover, I can estimate this area in a simple way, after all, in a simple way, because if U is non-constant, first, by this representation formula, I trivially, Cauchy-Bunyakovsky-Schwarz inequality, I trivially obtain this estimate. But then I can, I know an estimate due to Federer, basically, about the L2 norm of the winding number, and I obtain this inequality. And also, I can use the hard inequality I showed you before. This number for H piece, my God, so my time is over, is estimated, is estimated by this constant, where NH is written here, is this L2 norm of weighted L2 norm of basically the radial derivative of H. And in the existence theorem, our assumption is that NH is strictly smaller than 1. Since my time is over, I just want to say that, okay, Federer's type estimates also allows us to prove an estimate like this. It seems, and it is perhaps very technical, but this is the estimate that is used to show that if UN is a Pallas-Mail sequence under the assumption in the existence theorem, then this is bounded. This is of the order normal of UN, and this is positive, so this implies the boundedness of Pallas-Mail sequences, at least of the length of Pallas-Mail sequences. So it seems very technical, but it is important. And also by the inequality which is written here, I see that it is convenient to look at the energy functional as splitted in this form, because here we have something which is which grows, which is more or less the length of U. Okay, if NH is smaller than 1, then this is bounded from above and from below by the length of U, while by the classical isoperimetric inequality, the area functional with curvature H goes as the squared of the length, and it can change sign. So very rarely, the energy looks something like psi minus psi squared, and plus or minus, in fact. And so one can suspect the existence of a critical level of mountain pass time. And this is the case. Moreover, if NH is strictly smaller than 1, and H has this behavior of infinity, then by collecting all the remarks I said before, perhaps too quickly, we have a complete description of the behavior of all Pallas-Mail sequences for the energy functional. And so the end of the story is that if H satisfies all the assumptions in the theorem, perhaps otherwise it's too quick. So what is written here it is written that assume that some assumptions are satisfied, and in particular that NH is smaller than 1. And take any Pallas-Mail sequence for the energy functional. Then there are only 2 cases Basically, in the first one, the UNs try to become circles. Okay? This no, it's a rotation. Okay, don't forget this R is confusing. Up to a rotation, the curve parameterized by UN try to be circle, put it away at infinity. So in this case, the UNs are not bounded in the Sobolev space because the L2 norm goes to infinity, but at least you know that this lack of compactness phenomena might happen only at some very clear energy levels, which are L1/2, and 1/2 is the first energy level in which this lack of compactness might occur. Otherwise, UN, up to a sequence, converges to a non-constant H loop. And then occur now the conclusion of the proof of the theorem goes, let me say, quite in a standard way, once you have understood the behavior of Pallas-Mail sequence. I think I will stop here. Of course, I'm surely available to explain that this is more or less a standard mountain pass level. One can use almost standard arguments to say that if all the assumptions are satisfied, then the mountain pass level is strictly smaller than 1/2, which is the first level in which the Pallas-Mail condition fails. So the Pallas-Mail condition holds at the mountain pass level, and by nowadays, by the celebrated mountain pass theorem that there is a recurrence, this here is 50 years from the mountain pass theorem, from the publication of the celebrated paper by Ambrosetti and Rabinovitz. So 50 years. Okay, that's all what I wanted to say. Surely I want to mention two possible improvements or perspectives after this paper with Gabriele Cora. I have to say that I was really surprised of the fact that I had the opportunity to join two of my two different research interests of my life. One this kind of geometrical problem, and the other is apparently totally far, which is this field, large class of Hardy type inequality. So I found a joint point. It's funny. It's funny. Our hope is to do something similar for the more difficult and largely studied H-bubble problem. And also, I will try surely to understand something about the problem of prescribing H loops in the hyperbolic plane that is really very, very mysterious to me. Okay, that's all, and hence, thanks again.
Okay.
Thanks again.
Thanks, speaker.
Thank you.
And please, comments or questions. Okay.
It's a very particular problem.
Mm-hmm.
Okay. In any case,
Well, the particular problems are the most interesting, usually.
I stopped to study the H-bubble problem as well as the H-loop problem in 2011, because at that time I was thinking that it was not possible for, not only for me, I should say, to go through those questions without having any new idea. So it's 12 years, and I think that playing with this role of the hard inequality, okay, at least one can find some alternative, not better, but alternative existence results after 12 years. So let's hope. Let's hope for Gabriele mostly.
Okay. Okay.
Thank you very much.
Yeah. Well, if there are no questions, let's thank the speaker again.
And I hope to see all of you. To see, really.